Okay, so we are going to be doing some quantitative hedge fund exploration today. And the idea is to see if we can figure out Numerai. Before we do that, I'm just going to have some audio things here. Hopefully you guys can still hear me. Okay, so first of all, Numerai is a kind of like an anonymous community-based hedge fund game, data science competition. Basically gives you this obfuscated um, features of various stock market data, and then you can compete and by basically making predictions on that obfuscated data. And then there's like a leaderboard, and it's pretty cool. Basically, the board here's the leaderboard. You can see who's doing well and who's doing what. If you become really good, you're like Grandmaster. And yeah, it's not bad. Okay, I heard they're a little bit going through like some tumultuous periods. There's a lot of burns happening recently, but maybe there was just a few of the people. Yeah, you can invest if you, I guess, qualify as an investor, but they have their own token here. And yeah, so we're gonna do the tutorial today and figure out if it is a good way to learn about quant finance and machine learning at the same time. So anyway, just do the tutorial and let's see how far we get. Hopefully what we can get to today is something, actually, this is a new setup. I'm using Paint, the just Paint, not Paint 3D like I normally do. So this is going to be a bit different for me. To figure out, but let me see if I can quickly draw out what I want to achieve today. Actually, I like some of the new features. They finally have freaking layers. Can you believe it? Jeez, after like a decade of no layers, they finally figured out layers are important. Okay, so what I want to do is I want to have features that are drawn on. Okay, so I want to create a graph basically. What? Oh my god, okay, what the actual god. Okay, I can't use paint. What am I doing wrong? Brush, color, paint. Is not thick enough? What the F? What the actual uh no anti-aliasing. Are you serious? Oh my goodness. Why are we stuck in the past? Sorry for this initial rant. We'll get coding soon. Once I finish with my environment setup. Okay, so anyway, here's our graph, and what we're going to do is plot features along this axis. So there's obviously like there's different features, and just check like the value of those, but effectively we have like all these lines, which are the features, but it's going to be super densely packed. It's going to be like pixel per pixel. And these are going to be the eras, which is effectively the timestamps that they use in Numerai, which is like, I don't know, 1970, whatever, up until now. So the features are going to go here as like lines. And then what I want to do here is thickness. Thickness. Why is this so challenging? Let's zoom. OMG. Do I have to go back to old school paint? Okay. Shift. No. I can't believe I can't adjust the thickness of this brush. Absolutely unbelievable. Oh. This? No. Whatever the F. Okay, so anyway, so the point is the results that you actually want, the targets or whatever, are going to be like plus or minus like results, right? So effectively what I want, let's say this is just the graph of returns. There's going to be a lot of different stocks. Investable universe going to have all these different returns, profiles, whatever. So I'm kind of wanting to overlay. Oh, no, I get it. Okay, right click. Jeez. So I want to overlay the features here with the returns here. And then that's going to give us, I want to see if I can figure out that there's some kind of like macro trend that changes in the feature space with returns. So if we see like maybe a lot of upward momentum of returns in this period here, and then maybe there's a lot of like red feature space that's like prevalent in this period, maybe there's some pattern that we can think about. Ultimately, what I want to do is see if we can do transformer architecture to do these things. And the concept there is like you have next token prediction. I'm thinking we have next price prediction. Can that be possible? And you use the attention mechanism to spot periods of price action or feature space features or anomalies to help you pay attention to a specific period. Like let's say this period gets full of this kind of like similar red phase here, then maybe the attention mechanism can recognize this space as something that it should make different predictions on. Okay, that's the theory. Okay, so just basically doing some data science kind of like exploratory things. Anyway, so if you go to the tutorial, they've got a nice Colab you can open. And we're going to copy the code from here and stick it in here and then do some exploration. So basically what I've done so far is set this up in my Jupyter notebook and did all the basic stuff. I'm just starting with the small feature set and we'll train that and then go from there. I had a look at what actually gets downloaded. So in the features, they've got all these like named features, of which there's about like over 12,000. Right at the end of this JSON file, they got some analytics as well. Apparently, they've got these different target things. So we'll figure out what that is. So that's the only thing I've figured out so far. And okay, so what they've done here, just to make training a little bit easier, is they've taken the training rocket file, which is all the features. There's like a Spark kind of file format, Apache Spark, super efficient for tabular data. Not in focus. The light's a bit bright. Hey Google, make the lights 50%. Jesus, sorry about that. Okay, how's that? All right, good. I'm just gonna quickly double check that my audio is coming through. How's that? Cool. Okay, audio is working. Great. Now let's do. Okay, so there's eras, targets, and the set of features that's in the small feature set, which is only 42 of those 2,000 odd. Was it? Yeah, 2,000 odd like features. Just 42 of them. So let's see if we can train something there. Okay, so going back to the tutorial. By the way, I've got this new keyboard, so my shortcut situation is not going to be as good anymore because I'm still learning how to do this new super hacker mode locked in keyboard situation. There, the keyboard better your coding. That's what I always say. Now, okay, where did my, oh, I'm trying to alt tab. Alt tab. Wow, it works. Great. All right, let's put this here. So the next step is we're here. No, where did we get to? Wait, is this what I did? Yeah, I did this. Did this. Did this. Okay, so we've got train, and yeah, to make it more efficient, it's only every fourth era. Total training file size is over 2 gigs. All right, so now we want to train, which means we just see what's in there. Shift enter. All right. So what do we have? Okay, so we got these eras, and then these are the stocks. Everything's super obfuscated, so gotta like go with your gut on what you think is going on. Actually, you're not supposed to go with your gut. You're supposed to go with like hardcore quantitative reasoning. Use machines to learn what to do, not your brain. But I want to do the visual thing because I noticed that visual exploration is very powerful actually. Like your human ability to reason visually is probably more powerful than like data center of supercomputer cluster kind of stuff. So I'm just gonna do that. Anyway, okay. So the eras here, it's probably monthly eras or weekly, something like that. These are targets. So targets is I guess between 1 and 0. So 1 is super outperformed, or it's 75 is like outperformed. 50 is like you it's a market neutral fund. So basically 0.5 will be did the same return as the market. 0.2 is less than the market. So it's like a drawdown. It's like negative alpha, something like that. Okay, then these are all the features. And these features have numbers. Great. Lots of numbers. All right, we need to read what this is about. So what do they say? We have an ID is the stock, era is the date, target is the measure of future returns. Features describe the attributes of the stock, P ratios as an example. But I mean, P ratio is like probably the very first feature. Then there's 2,000 other features. It's probably like the movement of the planets and weather patterns and stuff would be a feature. And hopefully your machine learning algorithm can learn to ignore the irrelevant stuff. Otherwise, it's going to be trained on literally data that probably has zero correlation to returns. But yeah, it's always difficult. Okay, so as mentioned above, each era corresponds to a different date, 1 week apart. Okay, great. It is helpful to think about rows of stocks within the same era as a single example. You'll notice throughout this notebook and other examples, we often talk about per era. For example, the number of rows per era represents the number of stocks in Numerai's investable universe on that date. Yeah, so these are all the stocks in the Numerai's investable universe at era 1. That might change at era 2, potentially, maybe not. Sorry, slightly sleep deprived. Just had arrival of my first newborn son last week, so yeah, excuse my lack of coherent communication and potentially some baby noises in the background. Okay, anyway, plot the number of rows per era. Right, let's do that. Okay. This is matplotlib, I guess. I prefer plotly though, but we can change that over later. Okay, so obviously the size of the investable universe varies over time. 5,000, so yeah, that implies there must be some international stocks in there as well. Wonder. Let's see. Here's a hack when you have children, and you can't use both hands at the same time. Use this little guy that I've figured out. It's really cool. Windows H. Boom. See? This little thing here. Just hit Windows H and then it just types whatever you say. So you don't have to actually use both your hands to type. Delete that. Delete that. Delete that. Delete that. Okay, whatever. Select all. Select all. Select. Select that. Delete. Get in there. No. What is the number of investable stocks in the US stock markets? Enter. Select that. Delete that. Press enter. See, that's actually how I want to interact with these notebook assistants. Imagine it's just listening to you on the side like ChatGPT voice, and you can just chat to it. It's like, hey, what's up? What's this? Like, then you're doing your thing. You can ask it questions, like live coding with a peer programming kind of thing. Yeah. So I mean, I said doing like literally every single stock in the US, in both New York Stock Exchange and NASDAQ. I don't see how they can do 5,000 just in the US alone. Anyway, okay, so back to the tutorial. Target is a measure of stock performance over the next 20 business days. So it's not a short-term trading strategy, it's a 20-day prediction window. Country. Okay, so it must be international. For example, if Apple went up and the tech center went up, we want to know if Apple went up by more or less than the tech center sector. I think is it sector agnostic then? It's not just market neutral, it's sector neutral maybe. The hedge funds, because they often use leverage, no. Hedge funds, because they often take short positions, want to be market neutral. Because if the market's going down, they want steady returns in both directions. Generally, the classification of a hedge fund would be just the fact that they can take short positions. At least in the US, it's a bit more complicated, but that's generally what separates hedge funds and why it's considered more risky, or like more educated investors would have to be allowed to invest in hedge funds only because of the short position situation. Anyway, target values are binned into these categories. So this would be the type of machine learning you would do is predicting like a set of outcomes. And I mean, GPT architecture and like an LLM architecture is definitely not the recommended is not the recommended problem space for an LLM. But I thought about doing maybe the Carpathy 0 to hero on GPT from scratch as practice. So we might do that on a future stream specifically to train on this. Let's see if that'll work. Okay, again, heavy regularization of target values is to avoid overfitting as the underlying values are extremely noisy. Yeah. So regularization means that they have these 5 outcomes, and if they had more discrete outcomes or higher variation, it can train on like too many things. So those features are extremely noisy underneath, so they want to keep it like kind of simple. So this will probably show the spread of returns of those stocks. Okay, so 0.5 is by far the highest frequency return. Why is it 20? What's this 25 though? What's bins? Uh, uh, equal width bins to use for Instagram. Equal width bins. Data will be divided into 50 bins. Okay, so we can take that out. Oh, whatever. It's doing that, but it's not that important. Okay, so that's just to show the dissipation of those returns, which is very uniform. Uniform? Normal distribution, uniform distribution. Okay. What is the difference between a uniform and a normal distribution? I mean, I can say that way faster than I can type it, right? So how much more useful is this voice assistant LLM output thing? Yeah, sorry, not uniform. It's sound like a noob here. Sleep deprivation, not a noob. Okay. The features or quantitative attributes of each stock. Yeah. Obfuscated technicals. RSI stands for something index. I think it's like value. No, it's like momentum or something. You can see it here on let's take Apple for example. RSI. You put RSI in here. Man, Google stocks used to be so powerful. Now they just made it, they nerfed it so bad. Yahoo Finance has kind of like taken that over completely. Google used to have like all the indicators and everything. I don't know what happened. It's so crazy. Oh my god, this is unusable. This is unusable. What happened to Yahoo? Okay, let's see if I can put an RSI in here. Indicators. RSI. Yeah. So I don't know if you can see this in the dark mode, but this thing is going like this. So relative strength index. Ha. Yes, I think that's it. I think I got it. Okay. So now, underlying definition of each feature is not important. Just know that Numerai has include these features in data set because we believe they are predictive of the target, either by themselves or in combination with other features. Yeah, of course. And that's actually important. In combination with other features. Huh. 1 second. The 245-pound rep max back squat 2 days ago, so I'm in pain with this sitting position, but I'm okay to concentrate. Okay, feature values are binned into 5 equal bins. Okay, so 0 to 5. So all features also have a range of 5 values. So they kind of make it real simple. Real simple. Which is kind of crazy to think of the world of potential features you could use and how you would divide that into only 5 things. Seems like you're limiting the usefulness of what type of features could go in there. Okay, but anyway, so the targets are the features that you can, no, wait. Features are the data in these integer values that you can use to try to predict the outputs. So, okay, very simply, let's say here's the stock, this quadruple 7 stock at era 1 got 0.25, and this conscriptionist feature had a 2, this Wallabuff feature had a 2, Pensioner feature had a 2, all of these things had a 2, but the ataxi was 0. Okay, so if I'm just using my brain, right, then you can see, okay, this stock though, newbie, kind of like did well, and its features were the same as the first two, except the taxi was 2. So if I was just doing the human version of this machine learning approach, I'd say more taxi, more attraction of returns. And then if I continue my training, my human-based training, I can be like, oh, went down. Huh. Okay, but that was back in the day. Let's see if that still holds in present times, era 573. So theoretically, this would be low traxy, high traxy, low traxy. Let's see if I'm right. If I'm right, wrong. So the traxy feature has changed after all these eras. It does not mean what it used to mean. This is the problem. This is the problem of the stock market in general. It becomes harder and harder to predict because the market itself is a reflection of the market participants. And as the participants change their decision-making processes, so the market reflects that. The returns of the market reflect that. Also, look at the higher variation here in the modern era versus kind of very steady feature numbers in the early days here. So something is happening where there's some kind of consistency. But I mean, also these are different stocks, so I could just be talking up my ass, but this is the kind of thing that human intuition at these small scales could be completely useless. So we want to do machine learning to do the whole thing for us in mass and make sure. Okay, if data is a particular feature is missing for that era, more commonly in early eras, yeah, then all values will be set to 2. Okay, well that's probably explains that then. Okay. Which is the neutral value for that feature. Which kind of makes me think whatever machine learning thing we do, we should maybe just ignore 2s. Because they're injecting 2s into the early errors where there's no data on it. Should make a note of that. Ignore 2s. Okay, make a note of that. Ignore 2 in the features because let's try this. Back in the day, it was injected for features with no data. Okay. Not important. Just ignore it. Best ignore it because whatever it's going to learn on 2 is bad. Okay, so go back here. But you need to clean the data. You can't just have it as nulls, right? So that's always data cleaning is important. Machine learning. Okay, so let's do some more visualization. See what's up with this. Okay, what does this say? How does it know the data is missing? Wait, what? How does it know there's missing data? That's so crazy. What? It's just it's just taking the first error. It's just taking the first error and saying, okay, everywhere there's a 2 for the first error, that is the missing data. It's taking the last error. Okay, interesting. Is there so much that's just been way down here? How do I just ignore 2? Okay, it's not important to figure out here. I'll put other things to figure out. At a high level, our task is to model and predict the target using features. Yeah. You're free to use any tool or framework, but here we're using LGBM, LG Boost M regressor. Popular choice amongst tournament participants while you wait for the model to train. Watch this video to learn the tree-based models work. Okay, that sounds like fun. We can watch that together. So what is the tabular data set of our chief scientist? Alright, let's figure this out. So we're gonna train. The first time I get to use my new PC hardware. Let's see if this 4090 do some work. actually see that up here. So let's see if the GPU actually kicks in there. Okay. So what does code do? Apply GPM. It's going to take some estimators. So it's learning rate. Depth of 5. Some leaves. Following D parameters perform much better, but they require much more CPU and RAM. Okay, so we can compare this and this. And by deep, it's just doing more estimators, slower learning rate, more depth, more leaves, just more everything. It's interesting. This will take a few minutes. Grab some coffee. Oh, and I hear the kettle boiling. Okay, good timing. So let's hit go. Oh shit. Wrong button. Shift enter. What's wrong? What's wrong? I've also got Python 3.12, which is not, which had a version conflict with one of the recommended package versions, so this might be an issue. What is its error? Wait, what? Do I need to install something? Into Linux? No. Here's Light GBM. What? So I need to install this. God, really? That makes me very uneasy. I'm not doing that kind of stuff. Is that the errors we've got? What of them is this anyway? GPT-4 mini. Bloody hell. Cursor ass, give me some cheap LLM bullshit. I can't believe they pawned GPT-4 mini on me. Focus, please. Okay. What does it say? Open MP library. Okay. Why does it just seem I'm in Google Colab? That's crazy. It's probably because this is normally running Google Colab or something, so there's a lot of errors online mentioning that. Yeah. Okay. Well, was that the same thing that they recommended just now? Sudo apt-get install lightcomp 1. Okay. Yeah. Okay. Yep. Not even correct password. Oh God. Okay. Okay, let's try again. Out of focus again. Wait, where'd my code go? What? Dude. Got some action. Done already. Wow, the fans barely started spinning. What happened? What happened? Where's all my predictions? Got enough memory. So did it just finish? Is that the result? if I want to see the result. Wow, so interesting. Hmm. Yeah, okay, so it's very hacky. Anyway, okay, what is it saying? Add code to variate the model's performance. So here's the model. Here's the fit. And now let's see if we just stick this in here, what happens? Hmm. Feature importance. Bridal fingered pensioner. Oh my god, some of this stuff is disgusting. I saw some very racist shit in here too earlier. Yeah, I should definitely adjust some of these descriptors. But anyway, actual versus predicted values. This seems like so. Actual versus predicted. Huh. So if it's a model, I guess the model is just what's trained, and then you have the input output. Okay. Okay, whatever. Next. So let's test. Let's make some out of sample predictions and see how it did. Okay, so obviously the training was too small because of the amount of time this is taking. I'm assuming it's doing a larger set of features. No, same feature set. Okay. Here, data type target. What's data type? Yeah, what is data type? Oh, validation. Okay. I guess I got validation test. Whatever. Train, validate, test. So this is the validation. Delete validation. Data type. Why? I just take the data type out as a column. Okay. Downsample to every fourth error. Sure. Okay, so that's a couple things we want to do to test what we're doing here. So number one, these are the advanced versions, see if we can get more accurate predictions. So first is remove down sampling in training and validation. use deeper LGBN model to train on. Then also next would be use more features, small, then medium, so this will be one thing to do. This will be two things to do. This will be three things to do. Okay. Control tab. Oh, that works. Okay. By the way, I highly recommend this keyboard. It is so good. This is Voyager. It might be flipped for you guys, but it's the Voyager keyboard by ZSA.io. Is a very nice, very nice. That's like one of the most impressive companies, actually. Like the amount of attention to detail and how much they care about the product. It's like they're all in on like making it the best possible experience possible. Even the software they've developed, they've got like a game. It's just these people are passionate and it shows, and you feel it in the product. It's like you get to experience a bit of that passion every single day by just using the product. It's a nice experience. I wish more American companies were like that. All right, what are we doing? So is it finished training? Let's see here. Let's see here. Eras are 1 week apart, but targets look 20 days into the future. So we need to embargo the first four eras following our latest train era to avoid data leakage. Data leakage. Data leakage. Okay. Excuse me. Data leakage. Okay. So they've embargoed. Generate predictions against the out of sample validation features. May take a few minutes. Validation. Prediction. Model.predict. It's all built in. It's crazy. And that stuff existed back in my day. We used to do ML with pen and paper. Okay, validation. Error prediction target. Error prediction target. Prediction. Wait, why are the what is this? Why is the prediction? Is that like probability of this prediction? What is prediction? What is the prediction? What is prediction here? Like, why is that number what it is? Press enter. In the Numerai tournament, predictions are trying to estimate the probability or likelihood of a stock performing well versus poorly. Isn't that the target? Looking at the validation predictions in the output. Okay, the predictions are probabilities between 1 and 0. Yeah. Predictions are probabilities between 1 and 0. If that is greater than 5, suggests the model predicts higher likelihood of good performance. That is below suggests Model predicts higher likelihood of poor performance. What? I don't think that's performance. That's confidence. The actual targets are discretized. Blah blah. Predictions seem to be clustered very close to 0.5. It's not making many extreme predictions near 1 or 0. It's typical for financial predictions where being too confident can be risky. To better understand the prediction distribution, you could add. Okay. Damn. Do I need? Yeah, don't I need plot.show? Clearly, I do. Are those the predictions? Wait, so is target the the prediction was supposed to get, and this high this very many digit prediction value was supposed to get the target, correct? Press enter. Didn't get it. Change the window too quickly. Or I could just read the tutorial. Yeah, that must be what it is, right? Yes, exactly. The model is trying to predict the target values. Yeah, so it's just going super conservative. Super conservative. Which is a major issue in these things in general. Conservative, like middle of the road, basically. So, yeah. When the true target was 0.25, it predicted 5.1. Too high. 0.5. Yeah, and also because actually it's kind of obvious what happened here. Most of the returns are 0.5, right? So it just learned to always predict 0.5. Just learned to always predict 0.5. This is like a first round issue, like a first level of like trying to solve these machine learning problems issue is overfitting on the most common value in the training set. So maybe what you have to do is train on something like a more equally distributed set of results, or actually, let's see. This is a common issue with these types of challenges when the prevalence of a specific number is very high. The model just learns to always predict that number. What is the recommended best practice approach to solve this particular issue? Press enter. Come on, Sonnet. Come on, Sonnet. Tell me what to do. Tell me what to do. Weight samples inversely proportional to their frequency. Light GBM can use the sample weight parameter. Inversely proportional to their frequency. Light GBM can use the sample weight parameter to fit. Okay, so let's just try to fix this first because I don't like these results at all. This is horrendous. So let's first fix that. And then I'm going to fetch my t, which I'll probably have to rebuild the waterfall. So where's fit? This is the training here. Fit, okay. Understanding the majority class, oversampling the minority class, combination of both. Resampling techniques. Okay, stratified sampling. Ensure each fold in cross-validation maintains the same distribution as the original dataset. Stratified k-fold, custom loss function. Okay, here's an example implementation combining some of these approaches. Stratification. Numerai specifically, since it's a financial prediction problem, you might also want to consider using the provided error information for time-based validation. What? Focusing on relative rankings. Smaller. Focusing on relative rankings rather than absolute predictions. Relative rankings. Relative. Yeah, I guess. Relative rankings. Huh. You can like assume 0.5 and then you just want to make predictions off of that. Like up or down. Like are you just predicting up or down? It's like you make it binary. Evaluating performance using their specific scoring metrics like correlation. Okay. Is an example implementation combining some of these approaches? Should we just try this example implementation? Did I install sklearn? Yes, so. I know what that is. This is sklearn. Sample weights. So it does some balanced thing. Compute sample weights. So it computes the sample weights. Then it does the training. And then it has a sample weights thing. Then it has stratified k-fold. Train model on each fold. Train model on each fold. What if I just apply this? There's also another IDE called Windsurf. And by the way, I recommend Kagi. It is legit. Peak 90s Google search vibes. That's how I describe it. It is freedom. Oh my god, can Windows just get there? Honestly, I need to get that. I'm so close to downloading this freaking thing that lets you resize Windows easier. Okay. Windsurf. I used to windsurf. This is a new IDE. Better than cursor.ai. I don't like the signals cursor.ai is putting out there. Huh? Yeah, okay. But it's funny. They're like, their ads are based. Very funny. Okay. This looks too complicated. Train model on each fold. What do you mean train model on each fold? How do I implement that? Oh, you chain validate. Cross validation for folds. Oh, jeez. This looks complicated. Let's do. Oh, God, so complicated. Okay. Okay. Just give me the whole code to run. See, just speaking is better than doing this. My typing speed is atrocious compared to how fast I can talk. Let the TTS handle it. No, other way around. Speech to text. STT. Here's the complete code to implement sample weighting for the light GBM model. Why so much code? Model.fit. Okay, so this part is the same as this part. I think. Dot predict. Model.predict. Model.fit. Okay, so you set up the model. Actually, where are you setting up the model? Where's the model defined? Yeah. No. Yeah, okay. Reinitialize the model. Why do I need to reinitialize it? Just need to model.fit. So it's the sample weights thing that's the issue. Okay, let's stick it in here. Let's see what happens. We're going to, hopefully this class is installed. Yeah, seems good. Okay, so we want to do this SK fold thing to make the model not of index on the most common value, which is 0.5. So we're going to do an inverse proportional to class frequency. And we're going to try to get around Sonnet not being able to edit the code for us. I'm just doing some raw dog copy and pasting. I feel like a caveman not being able to hit apply here. Wait, what happened? Uh-oh. Oh, okay. So anyway, we've got the sample weights now. Sorry, sample weights. And the sample weights are going to go into model.fit. And then we train predictions. Oh, I need to run this, right? Oh, so quick. But what's... Because everything else is the same then. Trend predictions. Trend predictions feature set. Validate predictions. So what is all this? Did I get this from Numerai, or did I make this up now? Here's validation. This was some solid stuff. Here's the validation. Okay, so validation, train predictions. Still a model. Model.predict. I don't know what I'm doing. Let's just see. Let's just try this. Let's take this nonsense out because this is just some stuff I pulled from the internet. I mean from Sonnet. Okay, so now we trained the model, so we've got the model. This doesn't exist yet, so let's put it under here. It's also rubbish. Okay, so we've got the all of this. Let's see what this does. This is showing that the distribution is different between train and validate. I don't know what this means. I'm losing track of like reality. Yeah. Okay, so to see if it's less concentrated. Okay, well I guess it is less concentrated. No. Wait. Yeah, it is less concentrated. Yeah, way less concentrated. Okay. I don't do the down sampling thing though. Whatever. Validate validation is still defined there though, so it doesn't matter. It's the same validation. So the prediction is model.predict. Okay, so it's just predicting. So it's training's predictions. Okay. Validation's predictions. Okay. Whatever. Okay, so now let's get this thing here again. How did this plot this? This just did this, right? And nothing changed. Is that the exact same numbers? 4945. 4945. Model.predict. Validation feature set. Model.predict. Is this different? Oh my goodness. What's going on? So, validation. So new with machine learning. Just need to figure out what I'm actually doing here. It's just the embargo part. This is saying you model.predict validate on the validation. And then you have this validation prediction. And now you're just printing out the error, the prediction, the target of the validation prediction. So if you trained on that and you got this, then you trained on something different. Should get something else. Model.predict. So is that not this? Validation prediction. Validation predictions. I want to see just the table of predictions compared to the targets. Press enter. Yeah, result is validation. That's the same thing. Model.predict. I think I'm tired or something. I'm like struggling to figure out what's going on here. Okay. Did we retrain and make new actions? First retrain. Okay, I thought that we did retrain. Model.predict. Model.fit. And you take the results and the results. Is this wrong? I just want to see this. Oh. Okay, I see what I'll do. Okay. This basic array structure is messed up for me. So we just do this. And we stick that thing in here. Okay. So you see it's slightly better. Yeah, it's a lot better. Well, lot is kind of maybe an exaggeration. So why is the errors more? It's like added to the errors. No, wait, what? 51.7. Okay. So it's spread it out a little bit. Okay, it's not spread enough. Okay. That's the problem. So this, whatever it did to try to spread it, didn't work. Where did I do that spreading? Yeah. Sample weights were here. Try to compute the sample weights for unbalanced data sets. Okay, so balancing the data sets is kind of like the general issue with this kind of machine learning problem. Mm-hmm. Mm-hmm. Okay. But this didn't do that advanced thing that K, what is this cool advanced thing that was trying to do here? Stratified K-fold. So in this one, yet the sample weights was here. Yeah, that's the same. That's the same. Then you did this. Then you train. Show the complete example. Press enter. Yes, boy, press enter. It's obvious. Alright, so it looks like you train, validate or something. So what does it do here? So you put the sample weights here, which is balanced. And then you have training predictions, validation predictions. Okay, this is all just showing that. Print metrics by target class. Who cares? MSE by target value. Mask. MSE mean squared error. Calculate correlation by error. Numerai's preferred metric. Validation val preds error scores. Validation by group by. Apply. Lambda or coefficient, blah blah blah. What? Shows the initial target distribution, so sample weights to balance the classes. Trains the model on weights, evaluates predictions, visualize. I don't care about all that. Calculate the correlation. Who cares about the correlation right now? I just want to... No, it's not using that k-fold thing here now. What is this? Okay, what do you mean by train model on each fold? Ellipsis, ellipsis, ellipsis. Hey. Split validation, where you split your data into k folds. For each fold, use k1 folds as training data. Blah, blah, blah. Okay, train ID X, validation ID X. Split. Get the training validation data for this fold. Okay. Okay. Train the model on this fold's training data. Evaluate on this fold's validation data. Okay. Model.fit. So can you just keep fitting more to the existing model? Or use stratification in cross-validation. Or I'm sure this helps, but this, can we just do this as well? Sure, each fold in cross-validation maintains the same distribution as the original dataset. Maintains the same distribution as the original dataset. Generate the code to delete that. Delete that. Generate the code to specifically show me how to use the stratified k-fold thing. Press enter. Let's see. Okay. Okay. To convert continuous targets to what do we need to do here? We need to for stratification, we need to convert continuous targets to discrete bins. Oh, yes. Yeah, that makes sense. I agree with that. Store scores for each fold. Okay, iterate through the folds. Okay, so there's your model. It fits to that fold as training and validation predictions. Just get the metrics, print the metrics, Print the average scores across all folds. Oh wait, so the folds just saying you individually train on separate pieces of the data. Huh. Interesting. Explain what stratified k-folds is actually doing under the video. What is this approach about? Press enter. Yeah, the proportion of samples in each class is preserved. Basic k-fold just splits the data. Yeah, sure, okay. You might get unlucky and have uneven distribution. Stratified k-fold specifically first looks at your target variable distribution, then ensures each fold maintains roughly the same distribution as the original data set. Okay. Okay, 1 second. Sorry, I was on mute. Just showing you my baby. Developing some biological AGI here. Real time. Okay, so wait, stratified k-fold situation. And by the way, I'm going to be one-handed. Okay, let's see how this goes. So we are going to run this, see how it goes. It's gonna get kind of messy, but it's fine. It's fine. We clear out some of this stuff. This was the official tutorial. This was my let's just get that out of there. Okay, so let's just run this and see how it goes. Is my audio coming through fine now? It looks like it. What's the issue? The stratification you need to convert continuous targets to bin edges must be unique. It's 2.5. So how did they that? Second. Roll over. Sorry guys, 1 second. Just making a little spot here for the young'un. so we can do some live coding and live parenting at the same time. Okay. This is called hybrid work. Real hybrid work. Okay. What's it saying? It's saying that Sonnet 3.5 is being whack. Fix this, please. Fix this. Press enter. Okay, press enter. What does it do? Sorry. From our server. Alright. So it is doing something. Oh, shh. Come. Relax. 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 Relaxing. Relaxing. Yeah. So did it figure out what I need to fix? Because there are duplicate values in the target variable when trying to create bins. Here's the fixed version. Okay, what did you fix? Whatever. Don't care, just try again. No one's just using CPU. Interesting. Should theoretically use the GPU, right? It's crazy that it's not using the GPU. Crazy it's not using GPU. Like, surely that should be a default GPU thing. Anyway. Actually, let's check that. How do I get this to use the GPU? Press enter. Okay, device GPU. GPU platform ID, GPU device ID, tree learner GPU. Have a CUDA capable GPU. Install the GPU version. Oh, GPU version of LightGBM. Okay. Do I have CUDA toolkit? But these distributions still don't look much better. Still look trash. Okay, that's something we're gonna have to Google later. Did this really hallucinate? Did you hallucinate? Did you hallucinate about his GPU available? Press enter. What was that? Crazy. What actual is going on here? Wait, what? Dude, what is going on? Yeah. No, no. This thing is getting crazy now. Is this legit? It's not a 3.5. Doesn't seem right. Device GPU. Surely just this will make it use the device. Relearner. Is that even a thing? Read the docs. Do not want to read the docs. So I have to read the docs. Okay, time to read the docs. Light GPM. Oh yeah. Something enough. Actually, while I'm doing this, let's watch this thing. Oh my god.
Hi, everyone. Welcome to the second episode of Quant Club. I'm Michael Oliver. I'm the chief scientist at Numerai. Today, I just want to enter any questions people have about anything Numerai related and data science related, and also go over this paper. Why do tree-based models still outperform deep learning on tabular data? It's sort of related to a discussion we started to get into last week, and just an active area of research and something that is quite relevant to Numerai participants. So let's start with anyone who's attending, if anyone has any questions or anything they want to say before we get started and going into the paper, I'd love to hear that. You can just raise your hands or otherwise ask questions. Anyone know? Okay. Cool. Have people here read this paper? Any sort of, if you typically do quite well in tabular data. And so yeah, the reason I wanted to talk about this paper was because it's been known for a while that tree-based learners like random forest and gradient boosting machines typically do quite well in tabular data, which is fine and great. But neural networks, there's been a lot of really good research on them over the last decade or so that's seen them get state-of-the-art performance on many different types of tasks. But the sort of notable exception generally has been tabular data, at which these gradient boosted trees and random forests typically still excel. And people keep coming up with neural network architectures that they say are better or competitive with tree-based learners. But it's, as it seems to be often the case, that they don't do a really good job of creating these baselines for the models they're comparing against, where they'll put a lot of time into hyperparameter optimizing their new fancy neural network-based model, where they'll just use sort of very out-of-the-box parameters for a gradient for like XGBoost or something, and then say that they have a model that is better. The reason I like this paper is they try to be very fair to all the methods and do sort of equal hyperparameter searches for all the methods they look at. They look at a few different tree-based learners and a few sort of simple and also more recently proposed architectures in neural networks that are sort of designed to handle tabular data, and to do it across a couple different data set sizes that are sort of normal tabular data sizes. They are using a lot of the experiments are on a medium-sized data set, which is 10,000 samples. And they do show that sort of the gap does actually get a little bit smaller with larger data set sizes. And the question for Numerai participants is like sort of what is the data, like how does our data set compare in terms of number of samples? And there's a couple different ways of actually looking at this. I mean, we do have a couple million rows, which makes you think maybe it is actually a much larger data set than this, like a 10,000 sample. But there's a particular interesting structure to our data that makes it a bit different. The eras are sort of the relevant unit of data in a lot of ways. And we only have a few hundred of those because you're trying to predict well in each era. It's the samples are not kind of really independent in sort of a standard way. And so it's not like you have 2 million different samples, and all that really matters is predicting any given sample correctly. What really matters is your performance per era. And so when you look at it that way, you might say that we only actually have a few hundred samples. And so maybe it's actually quite a small data set. So I think some of these the papers like this are quite relevant, looking at the sort of medium and small data domain to Numerai in particular. So another thing I liked about this paper was that rather than just saying like, oh, this method works better than this method, they actually try to investigate what it is about the method that gives it a performance advantage. What are sort of the inductive biases of tree-based learners that seem to help them with tabular data? And they try a few different experiments and give some good intuitions about that. So let us dive in. So they're just sort of introducing the problem and setting it up. They are using sort of 45 different tabular data sets, and they're not particularly high dimensional. Ours is higher dimensional than most of these, and they're trying to basically clean it up and make them all sort of the same thing. But it's nice that they actually sort of release this and have sort of this tabular benchmark that they have are releasing for people to use and compare in future papers. Hopefully people take advantage of that so that when they come up with new deep learning based methods that are for tabular data, they have a sort of better basis of comparison. We'll see how that actually plays out going forward.
I feel genuinely nervous to release this to the public. If you are a coach, a service provider, or you sell any kind of
okay. So here are the set of models that they're benchmarking. They're benchmarking a classic multi-layer perceptron, and just using slightly fancier learning rate scheduler, but really just a very simple MLP. A ResNet is basically just a sort of upgraded neural network with some fancier things like batch normalization, and ResNet means it has skip connections between layers.
Only have one
That's basically
GPU.
just an identity. So a layer is basically just the output layer is its output plus its sort of input, or the input from a couple layers back. It's just a method that allows gradients to sort of flow better through a network and makes training neural networks a bit easier. They're using, and then two sort of transformer-based models that are specifically designed for tabular data.
Oh, interesting.
And they make these really nice plots, which are in terms of number of random search iterations. So they're basically this axis is sort of how much hyperparameter optimization they're doing. And on the y-axis, they sort of have this normalized accuracy, and you can see that basically all the methods improve as you do more hyperparameter searching, which is not surprising. But in both the classification and regression tasks, you see that basically XGBoost in green, the gradient boosting tree, which is basically the scikit-learn's gradient boosting library, tend to do the best in classification and regression tasks. And so this is using only numerical features, and this is using numerical and categorical features, and even random forest with more hyperparameter optimization tend to do better. All of the neural networks are here at the bottom. The very simple MLP is the worst, followed by ResNet. The two sort of tabular aimed, more complicated transformer-based models tend to be somewhere in the middle, but generally they are still sort of quite a bit outperformed by just sort of standard tree-based learners. And yeah, that's basically the pattern you see all throughout this paper. And so the question is, why is that? Why do tree-based learners do so much better on both regression and classification tasks? It doesn't seem to be just due to numerical features versus categorical features. There seems to be something about the inductive biases of these methods that just help them work a lot better sort of out of the box than any of the neural network-based methods, even accounting for hyperparameter tuning. So one of the things they do to try to get at this is they smooth the output. The idea being that, let's see. So yeah, so if you basically smooth the output of all these models, how does it hurt the performance? The idea being that a tree-based model might be able to learn sort of less smooth functions, like neural networks might be biased towards smoother functions that might work less well out of sample, and that the tree-based models can make sort of arbitrarily disjoint and have sort of sharp edges in the functions. And so if you smooth the output of them, how does that hurt the performance? And so they do this with this Gaussian kernel smoother. And this is just basically increasing the amount of smoothing. And this is the normalized test set score. And so you see that smoothing the output of like the gradient boosted tree or the random forest hurts the performance quite a bit. The gradient boosted tree and the random forest have some of the best performance when they're not smooth at all, or at 0. But then as you smooth things quite a bit, all the methods have very sort of similar performance, and the drop-off for the FT transformer and like the ResNet is much smaller, and they end up at a sort of very similar place after smoothing. So this suggests that it does have to do something with the smoothness of the output. These neural network-based models are giving you sort of smoother outputs that is actually hurting their performance, and the tree-based models are sort of making these much sharper functions that help with generalization performance. So that's sort of, yeah, we do know that neural networks sort of prefer smoother things, but it's kind of amazing how much that seems to hurt their actual performance on a lot of these tasks. So this was this first finding neural networks are biased towards overly smooth functions. Let me see, I think there was a fun plot of that somewhere in here.
Easy.
I guess I would argue that empathy is a job.
Okay, me too.
Yeah, so here's an example of what that looks like. This shows the decision boundary of a multi-layer perceptron versus a random forest for two of the most important features on one of the data sets. And so you can see the multi-layer perceptron has this decision boundary that is very sort of smooth and very, where the decision boundary for random forest is much more complicated and has this little islands of things that things with
so interesting
on each side. So it's sort of able to isolate maybe much more complicated interactions between things, where these neural network-based models are not able to capture this sort of very fine structure into the functional relationship between things.
Damn, that's crazy.
Okay.
Such a good paper.
Let us move to any questions so far?
Hey MDO.
Yeah.
The sort of fine structure, you said that it can't be captured. Does that just go away when you have a lot more parameters for the neural network?
Probably not completely. It definitely helps to have more parameters. And at sort of the limit where you can sort of over parameterize something and fit the data perfectly, it probably goes away to some degree. but yeah, there's still going to be this bias towards smoother functions, just sort of due to the structure of like rectified linear units and linear combinations of features and whatnot. Any other questions? Okay. The next thing they look at is how unimportant or uninformative features affect the different architectures. And they use basically a random forest to compute a feature importance metric for all the features, and then sort of remove features either randomly or based on this metric. And see, and also basically adding just noise features. Let's see. So yeah, so this is a plot showing that as you remove features in decreasing order of random forest important, that your the normalized gradient boosted tree test score basically gets worse and worse as you'd expect, but quite slowly. And this is basically comparing a few different methods. Let's see. And also, so yeah, let's see. So removing features going from 0 to 75% for the 4 different methods. Basically, removing features hurts all the methods. It hurts, and let's see, this is, and this is also percentage of uninformative features added. So this is if you add a bunch of sort of noisy features to the data. I think this one is maybe a little bit more informative in that you can see that as you add more and more sort of just garbage features, it hurts the ResNet the most. It hurts, and it hurts the other methods sort of roughly equally proportionally. But yeah, both the gradient boosting tree and random forest are sort of least sensitive to having these noisy features added. But there is, let's see.
Oh, clean. Every time I say something. It's okay, relax.
But yeah, I mean, basically the point is MLP-like architecture are not robust to uninformative features. And one of the reasons is that MLPs especially are just sort of linear combinations of all your features. I mean, all the weights are learned, but you're sort of starting off with random weights, and so you're the first sort of layer is mixing to some degree all of your features. And so as you add more and more uninformative features in the first layer, it just sort of pollutes what is being learned in each subsequent layer of your multi-layer perceptron. And so having good feature selection is especially important for things like MLPs. It's yeah, I mean, having uninformative features hurts all architectures. So features important, feature selection is important for everything, but it's especially important for multi-layer perceptrons.
Okay.
But the thing that I think is sort of most relevant and interesting is this idea that the data are not invariant to by rotation, so neither should be the learning procedures. And this sort of goes back to this idea of what MLPs are doing in the first layer. And so how they sort of evaluate this is if you basically put all your features through a rotation matrix, which is basically just sort of, yeah, basically just linearly combining them in all sorts of different ways, maintaining the same information, but your new dimensions are just sort of all your features mixed together in various ways. So you just sort of rotated the space, which is essentially what the first layer of a neural network is doing. But what you find if you do that is, if you do no rotation versus rotation, so if you just keep the data in sort of natural form and don't apply any rotation matrix first, you see the pattern where the gradient boosted tree and random forest do quite a bit better than the other methods. But if you apply a rotation matrix and sort of are linearly mixing all the features together before your learning algorithm, you find that actually the neural network architectures do better than the tree-based methods. So the mixing things together actually seems to hurt the performance of gradient boosted trees and random forests. And people have seen this in the tournament to some degree, like when people are doing like PCA on the features and then trying to do learning after that. Especially if you do a tree-based learner after running PCA, it tends to not work very well. And so yeah, this is a good reason why. And I mean, and the way I see what and what they describe happening is you are sort of mixing features that have very different properties. Maybe you can think of how good of a feature it is, like what is the sharp of an individual feature. And if you're mixing features with all sorts of different properties, how well they relate to the target, their individual signal noise, you're kind of mixing good features in with bad features. And a tree-based learner is able to kind of look at features one at a time. It's literally at every split of a tree, it's evaluating a set of features individually and deciding where to split. And so its ability to consider features one at a time is sort of lost after you do this rotation, like a PCA or something. And so yeah, so it is kind of interesting that these other neural network methods are hurt a little bit by rotation. The ResNet's not actually hurt at all. And that suggests, yeah, I mean, the first layer of ResNet is reducing the rotation itself, and so another rotation isn't hurting anything. The transformer model is hurt a bit by rotation.
Testing.
Suggests that transformers are better at not just mixing things together through their intention mechanisms, able to kind of select features that you consider them more individually than just sort of having everything mixed together. But there's still a fair bit of mixing within them, and which is why they're not sort of doing as well necessarily as the other methods. So those are kind of the main points of the paper. They do perform a bunch of different experiments and sort of show how across different data sets. They have a lot of plots here at the bottom, sort of just showing different training sets. And here's like a large training set. But you still generally see the XGBoost is very, very hard to beat across a variety of different data sets. I would love at this point just to have people ask me questions or share any sort of their experience with these things. I know JRB has actually had quite a bit of luck in actually using neural network architectures in his Numerai work, and I'd be curious to hear what he has to say about this, and if he has any sort of tips for people for using neural network architectures, whether he thinks it's sort of feature selection that is important, or just sort of more architectural things in trying to make neural networks have some of the better inductive biases that tree-based learners have. JRB, are you here? I don't know if you are here. Okay. Does anyone have anything they want to say or any questions they want to ask?
Michael, you were showing how the feature, adding bad features hurts models, right?
Yes.
Adding noisy features, it hurts neural networks and it hurts gradient boosted tree models. But gradient boosted tree, less so. Do you think that that's also, I mean, I think some people in the Numerai tournament kind of think, well, Numerai's prepared all the features, therefore we can use all of them and should use all of them. But maybe this is saying, well, if you can remove a few of them, that could be very, very helpful. Do you think that's true? Like basically feature selection is a very important thing to do well.
I do think I mean we try not to include like garbage features, but there probably are features that you could would maybe do better without. I mean we sort of are biased towards giving people more of the data and more giving them sort of more options, because we don't want to sort of say that we know for sure a feature is garbage or not if we think there might be some value to it. But yeah, I mean I do think feature selection it sort of depends a lot on the model, and so different models seem to do better with maybe different features, and which is why we wanted to include more features. So I think feature selection is something people should take very very seriously. I mean, and also it just like it will greatly reduce the size of the data you have to work with, because we have quite a lot of features, and it can be a bit cumbersome to work with sometimes. And it will also make your models more unique. If your model's using a different subset of features than other people, it's more likely to like have true contribution or something. But yeah, I mean. It seems like if there are features that are actually just garbage features in there, which seems totally possible, you would be helped by doing some feature selection, just because having garbage features will degrade your performance a little bit.
What is your best way to do feature selection? What do you think is the sort of state of the art way to do feature selection on Numerai?
Yeah, so I had a forum post using Baruda Shap, which I think is a pretty good feature selection method. It is quite slow, and I posted a set of features that it came up with. I think that's what is in our like small feature set. And I mean, no feature selection method is perfect. One thing with the Baruda Shap is it is sort of dependent on what model you use for doing the feature selection, because it is basically adding. It's basically like one of the things that's doing is like adding fake features and looking at how your like Shapley values on the fake features compared to your real features, because you would basically think that fake features shouldn't have any feature importance. And so it gives you a sort of nice baseline for, is this a real feature? If it has a feature importance that about is the same as a fake feature or worse than a fake feature, it's definitely not really helping. And that's a sort of a root idea, and the Shap part is just using the Shapley values as the feature importance metric. I think that's a pretty powerful method, but you do have to kind of be careful with it, because it is sort of giving you a set of features that work for the model you're using at each iteration, and those set of features won't necessarily work as well if you change the model after that.
ChatGPT's got voice mode built in. I want to use LightGBM Python package with my NVIDIA GPU. What do I need to install in my WSL Ubuntu environment to make that happen?
Install these packages. 1. sudo apt install y, build essential, cmake, libopenmpdev, pip install lightgbm, optional. Pip install kupi CUDA xxx, replace xxx with your CUDA version.
How do I know CUDA's not already installed?
Run nvcc -- version in your terminal to check if CUDA is installed and to see its version.
Not installed, so how do I install that? Do I need to install that?
Yes. Install CUDA by downloading the appropriate version from NVIDIA's website and following their installation instructions.
I think CUDA's on my system, but it's not in my WSL. Or if I installed it on my system, would it be in WSL?
No, installing CUDA on your main system doesn't apply to WSL. You need to follow NVIDIA's guide to install CUDA in WSL.
Okay, can you just tell me how to do it, please?
Sure. Install the CUDA toolkit in WSL by running wget https developer.download.nvidia.com/ubuntu 2004 x86 64 CUDA-ubuntu.
Okay. Thanks, ChatGPT. Thank you a lot. GPU for the next stream at this point. That's ridiculous.
So that's an important caveat for that. Yeah, I mean, there's a lot of sort of feature selection methods that like Marcos talks about in his book, like mean decrease accuracy and sort of feature permutation ideas. Sort of looking at if you remove or like permute a feature, how much does it hurt your out of sample performance? I think those are all great methods as well.
As you said earlier, the like era is a kind of a fundamental unit on Numerai.
Right.
And none of those methods use the eras, I guess. But I guess
No, but
something like
adapted to, yeah.
Yeah, because I think there was that presentation in a New York meetup, Numerai meetup, where it was shown how I can't remember who did it, but it was shown how you can compute the sharp of each feature, and use that as a method to select good features.
Yeah, I think that's a great way to sort of just select the if you're just looking at the features and their sharp with respect to the target, that's a sort of good first pass. I mean, doing something like that kind of misses potential interactions that might have like higher sharp. I mean, there might be a feature that by itself doesn't have a good sharp, but when you condition on it, gives you something that actually does have a very high sharp. If you basically some other feature given this feature's value, so this sort of interaction might actually have a much higher sharp value, and you would miss that kind of thing just looking at them one by one. And that's where things like the Shapley values are much better at kind of teasing what are the important features out, because they sort of are in terms of a nonlinear model. But yeah, I think trying to do all your evaluations error-wise is important, and you can they have a much higher sharp value, and you would miss that kind of thing just looking at them one by one. And that's where things like the Shapley values are much better at kind of
That takes into account all yeah, this stuff's easy, man. Damn it. I should have been quant finance more regularly. Okay, so yeah. Shapely value. Use shapely value.
teasing what are the important features out, because they sort of are in terms of a nonlinear model. But yeah, I think trying to do all your evaluations error-wise is important, and you can adapt all these methods to, so you could compute like the Brutus shaft like per era or something, or compute whatever metric you're deciding for per era and then average, or find like the, yeah, it's and then it's also a question of like how do you select, if you are computing the statistic per era, do you do something like a Sharp, like the mean over standard deviation, or do you want to find like the best, like worst case scenarios, or like find the thing that has, because like basically you'll see a lot of variance era to era. And so do you want to sort of like minimize the worst case scenario? That's another sort of way you could do, rather than just selecting the one that has a like based on the average, or like Sharp, like look at the minimum. Wiggle mused.
Yeah, so I guess the big question, well, everything you say is correct, of course. And I've noticed all this, for years, trying to get good core, and MMC also in the old days. And it has to do with the inductive biases, and not sort of using those statistical mixing methods like PCA, at least to replace the data. I think it can work if you augment the data with it. This can make more features. Although I used to say that, and then someone would come along and say this model uses PCA, it's it's rank number 4 or something. So I'm often just not doing the correct thing. But in this age of TC, the question is, what is good performance? Because it seems like this it's doing better with trees and so on. Is that sort of measurable validation, things we can validate with core. But with TC, it's just all over the place. I mentioned this last time. I mean, I've got a model that was made with B3 data, made to get core and MMC, and it's humming along. It gets core. It hardly ever is got a negative core, and it sucks at TC. Once in a while, it crosses 0 and then goes back down, but it's just no good at TC. And we look at the leaderboard, and we see most of the highest models on TC do have pretty decent positive core, but they are not the highest core by any means. And we also see, if you go looking, we see plenty of decent TC models that are not getting any core at all.
Compensation.
And I mentioned, yeah,
Total,
so I mentioned this
total
last time.
correlation.
I started getting good TC on some models when I started messing with the data set and doing that sort of statistical mixing, and basically my whole approach now is just like a shotgun, where I am, it's not random, but I'm picking out every inductive bias I can think of and trying to make a different model with a different inductive bias and based on these things, and then just see how it shakes out. So like I said, everything here is correct, but I wouldn't necessarily take that as discouragement to do these other things, because that's where the gold is possibly still. So
yeah, I mean, I think and I think a sort of good, what you're doing is sort of the right thing, and just starting to think about what are the inductive biases of your learners, and trying to see what inductive biases seem to work for this particular problem.
I always thought that way, but nothing ever worked other than sort of a straightforward thing. And all these models I'm making now, they're generally terrible at core, from what I can tell.
One other inductive bias they didn't mention here that has always seemed important to me, between tree-based learners and things like neural networks, is the extrapolation inductive bias. So tree-based learners extrapolate sort of in a like piecewise constant way. So like if you just think of the most simple tree where you cut your space in half, it basically assigns one value to one side and one value to the other side.
Right. Anything over that border is just the same as the border, right? So
exactly. So so everything in that half space gets the same value. So it's sort of this piecewise constant. Whereas like an MLP or neural networks will generally have a sort of linear or like a piecewise linear inductive bias. So your extrapolations kind of continue in a sort of linear way outside of the data. And so you can see like in this plot, there's this decision boundary sort of is slowly changing over this, which is sort of just indicating it's due to partially to the inductive bias of the MLP, where it's basically just this piecewise constant function over the space. And this is hard to think of in high dimensions, and all this stuff is actually happening in high dimensional space. You can sort of visualize it in 2-dimensional ways, but what generally happens in our like very high dimensional space, we're usually in a part of the space where we've never been in before. Like a new set of features is pretty far from any set of features that we've ever been in before. And so how your model generalizes to this new point in this high dimensional space seems to me pretty important. And whether or not a sort of piecewise constant inductive bias and how you extrapolate to this other place is better versus like sort of piecewise linear, it's sort of, and it might be different for different features. Like maybe a piecewise constant for some features is a better inductive bias for extrapolation, where a piecewise linear might be better for other features. And so like the meta model, or sort of mixing all these together and hopefully getting sort of like a better inductive bias overall. But yeah, I just wanted to highlight that other inductive bias difference between these types of learners.
That brings up a general question I I've wondered about the data for a long time. We get the data, of course, not in raw values of any kind, but buckets, and the buckets are always the same. So you would think that at least with some features, the raw values are, not necessarily equivalent. In other words, from era 10 and era 1000, some feature, it's like it's recentered and rescaled. So is it real? Does that make sense? Like the 0.5 value for era 1000 at a feature could be quite different, or is everything are all features sort of inherently relative anyways?
It's more like the latter. Yeah, I mean, we're turning everything into basically just everything being relative. Because because we care about in the end is sort of the relative ranking of stocks, rather than like their absolute performance. So we turn all the returns are in sort of relative terms, and all of the features are in sort of relative terms.
And that's something I've done myself when, like if you have a model where you need to scale the data just to get it into the model, you z-score it, say, you're supposed to save the mean and the standard deviation of the data that you use to put in the model to transform your new data, right, to get it in that same space. And I do that sometimes, but other times I'm just going to scale it on its own terms, and then call that equivalent. And sometimes it works better. So I've actually done quite a lot of that. And sometimes it's quite extreme where I'm, like you do a PCA, you're supposed to make the data like the original data, but sometimes I just scale it on its own terms and then apply the whatever. And it works quite well, and quite different than if you did it the other way. It's like a whole new inductive bias that way. And then again, with TC, we really need to be able to validate our TC. So I hope that sort of thing is coming. When I make it a core model, especially with all the data we have now, I mean, you can tell more or less if it's decent, but you can make a very good core model and it's just size of TC. You can make it, and then you just put something forward and you just got to wait. I hope we can get some tools along those lines.
I wanted to ask, I know people now have access to like past meta model scores, and I wanted to ask if people have had luck in using them and trying to pursue TC-based models and been able to make sort of more sense out of TC now that they have access to like past meta model scores.
I just started looking at those in the last week. I was actually going to use them, I think a lot of people are, as target or residuals for target, or as some form of target adjustment or something, just because it's a new thing.
Yeah, this relates to.
Even if I had made a model, I mean, we've had them for a month or something. Even if I had made a model, I would have no idea still, because the TC can be so random that you just don't know until you got like 20 years or so.
Yeah, I mean, so this relates to that question somebody had on Slido about if we could give sort of the optimal TC predictions, sort of like what an optimal prediction for TC would look like.
Yeah, what would be a perfect TC or something?
I mean, it's a bit hard to answer, but I think a good sort of proxy would basically just be something like you said, residualize the targets to the meta model scores. Basically, just do like just do like a neutralization or like Gram-Schmidt orthogonalization of the. You're just subtracting off from the target the part of the meta model prediction that is correlated with the target. It's a very small part. I mean, the correlations are like 3% or something. So you're only so you're not changing the target that much by subtracting off how the part that is similar to the meta model. But after doing that, if you sort of redo, if you train towards this new residualized target, that would sort of be like if you were able to get that perfect, that would sort of give you perfect TC, or sort of like the highest possible TC. Because that target is created like from returns and will have returns that are orthogonal to where the meta model is pointing you, and so it would give you extremely high TC. Obviously, it's going to be hard to do because there's the meta model has a lot of the information that is sort of learnable from things, but residualizing to the meta model scores seems like a great way to try to get at TC.
Yeah, well, I mean, is there a solid suggestion there? And let's say I build a model today. What can I do to see if it's going to get TC, save submitting it and waiting? If I look at those meta model scores and look at the residuals, and then the core left over is good, would I then expect to get TC? It's hard to even tell because TC doesn't even have a target, right? We have these targets, but it's not like it's the residual of the NOMI, as people sort of complain about, right? So they're like, hey, I got a good core, and then where's my TC?
No, it is for sure tricky. I mean, if you look across the top of the leaderboard, which is sorted in terms of TC, you can see that there are sort of different strategies that work. I mean, you see some people that have that are near the top of TC have extremely high correlations to like Jerome 60-day target, which is one of the reasons we put that on there. But you see like some of the people who are doing very well on that target are doing very well in TC. You see, one thing you generally see is a lot of the people who have high TC, their correlation to the meta model is like 50% or under. That's I mean, to have like the absolute highest TC, you clearly need to have very low correlation with the meta model, but you also need to be.
Meta model is what Numerai uses to actually make the stock market predictions. So it's a combination of everyone's model, like mushes it up and then uses that as its model. But the weighting it uses is clever. It's a betting based prediction weighting mechanism. So the people who put the most money behind their model is like a confidence score of the model, and then they use that to weight the meta model with everyone's individual models. And then TC that talk about there is something like total correlation with the meta model. And then what they want is if your model is different to everyone else's, that is valued higher. So there's some kind of like extra score you get for TC. And then there's actual contribution. No, it's total contribution. I think it's contribution to the end result of something like that. But there's correlate. All I know is that this correlation is important. So they want like idiosyncratic models and predictions, and then the actual contribution of your model to the results is also measured somehow. Yeah, so kind of sophisticated in that way. Okay. Please explain MSE R2 and whether these results are good or not. These scores, are they good or not? Press enter. Mean squared error.
Giving a signal that is consistently good over time. You need to have sort of consistently positive core, consistently while being uncorrelated to the meta model. And yeah, there's going to be variance week to week just depending on the markets, and it's a bit more volatile metric, and so you do need to give it some time. But you see that people who are consistently have positive core while being very uncorrelated with the meta model are often doing quite well. And it's kind of hard to say like how to get TC because clearly there's multiple strategies that will work.
Right. Do you think that if you are not getting good core, even negative core, that you're just not going to get TC, or whatever TC you are getting is spurious and random, or is the sort of good core correlated with good TC just a subset of the good TC space? I mean, the models I've been making run from 0 correlation with the meta model to about 24% with the meta model, and those are more normal. A lot of them are just 0. They get negative core. Sometimes they get, I mean, the core just seems random. And then I'm just sort of hoping that the TC is good. I mean, I don't expect it to be, super consistent, but if it's good 60% of the time, it's profitable. So is anything like that probably just nonsense, or you think there's something that could be in those spaces?
I would expect that if your core is like on average 0, it's likely to be just noise.
I mean, I'm positive some of them are, but some of them are very interesting, and they go,
I mean, it's also worth looking in the tails too. I mean, if you are getting sort of positive correlation in the tails, and it's worth looking at. If maybe you get 0 correlation overall, but if you get positive correlation in the tails consistently, then you would expect to have good TC as well.
Right. Then I have to test that myself later.
Yeah. So yeah, I mean, the tail effects are especially apparent in TC. Our current correlation scoring is sort of too insensitive to the tails, and we're actually planning to move to a newer version of correlation that basically a Pearson correlation on like Gaussianized rather than because our current correlation scoring, we rank normalize your thing and then do correlation, Pearson correlation with the target. We plan to sort of move to just like a Gauss rank version, so we're just Gaussianize things, which will emphasize the tails in the correlation score as well.
Well, I mean, NOMI moving from a flat target to NOMI Gaussian did that to some extent, right? So now you're talking about doing that to our side as well.
Yeah, exactly. Doing that also has a nice advantage of the correlation metric can actually go basically up to 1, because right now the sort of mismatch in the distribution sort of caps the correlation score at like 0.92 or something.
0.91. Yes, I brought this up a long time ago.
Yeah.
You said, he'll never get there anyways. It doesn't matter.
No, exactly. It practically makes no difference at the levels of correlation we're at, but it is a nice property to have the metric actually be able to go between 0 and 1. And the new metric we're going to be moving to at some point we'll do that. Yeah, I mean, this will probably also come with some new targets as well. We'll probably move to a different scoring target at the same time, but there'll be plenty of warning for all of that. But still,
switching topics, you were talking about feature selection, and how you probably need to drop some, or maybe some are garbage or whatever. I was just looking at something a couple of days ago that was, I think, was using genetic algorithms to find subsets of features that work together. So rather than picking some one at a time, where I think you're going to end up with the same thing, because there's a lot of redundancy in the data. So there might be this set of features that go together in a sort of a similar but overlapping but different set of features, and you kind of need to drive yourself to one of the other subsets. And if you always start at the top or the bottom and add one at a time, you're going to tend to get the same ones probably. But there are some other ways to do it. But I think almost all of the really good methods for feature selection are inherently, like you were saying, tied into the model you're using, because it just matters so much what the inductive bias of that model is.
Okay, so while these guys are yapping here, looks like the depth of my thing is the problem here. So in order not to waste time overall, I think I should get NVIDIA GPU setup stuff working. So I'm going to do that sort of long. And then we'll see how we get in 5 minutes on getting that set up.
So I think everyone has to sort of find that solution for themselves, where they sort of pick the model they're going to go with.
NVIDIA CUDA installation Windows.
Or try out and then look for those subsets.
Yeah, exactly. But yeah, there are a lot of like good packages and ways of doing these now. But as I said before, I think using error-wise statistics is probably very helpful for doing feature selection, because it is our problem is a bit different than most data science problems in that we want to be good sort of at every era rather than every sample.
Yeah, and I think a problem with a lot of the methods, and possibly with this whole paper actually, is that it's better, but it tends to become kind of linear. And we've got this thing where we sort of want to avoid linear just because it's linear, so that's sort of a Numerai wrinkle to these sort of, this is better than that. But what happens when you force it to be nonlinear response to the features?
I mean, well, yeah, I'm not sure what you mean by it becomes more linear. I mean, so like,
well, I mean, you get more feature exposure that
okay.
You're going to neutralize out.
I mean, yeah, I think like MLPs and neural network-based things, I think will generally take on higher feature exposure since they give sort of more linear answers overall. I mean, there's been papers for a long time just sort of showing that neural networks are often way more linear than people think they are, or they have really large linear regimes where they're well approximated by a linear model in various parts of the regime. Like in this plot I'm showing here, you could see that it would be much harder to approximate this random forest decision boundary with a linear function, where you can imagine a linear function would actually approximate this MLP decision boundary pretty well.
But with that mixing, you get a de-emphasis on individual features, and random forests or any kind of tree can tend to fixate on very specific features that you need to dial it back on at times.
But in a particular way, I mean, your feature importance isn't the same as like linear dependency. Yeah, you could potentially have a feature that has very high feature importance, but actually isn't that correlated to the output of your model.
Do you think that's still a problem? Maybe just a high dependence. If this feature, even if it's nonlinear, is just not behaving this week, then there goes your model.
Yeah, I mean,
in terms of robustness.
Yeah, there's definitely. I mean, if a lot of your, I mean, it's sort of saying like how dependent are all of your splits and whatnot, are sort of how is the sort of output of your model dependent on what the current feature value. Yeah, if that feature starts behaving very differently, it can still kind of mess up your model. And yeah, we the sort of the way we do like feature neutralization is kind of a linear hack. And in some way, you maybe want to sort of balance feature importance, the sort of nonlinear dependence on things, and make that more balanced across your features. The hyperparameter we use to help that is like the call sample by tree, where you're basically for every tree you're only looking at a subset of the features. And so when you do that, each tree is only looking at a subset of the features, and so you tend to, over the set of trees, use each feature a bit more and sort of tone down how much you're using any one feature, rather than if every tree could look at all the features, it's always going to pick the best features. You're going to get a lot of feature importance for like the best features and take a lot of feature risk that way. So this sort of that hyperparameter helps with it, but there isn't explicitly a way in these boosting algorithms to sort of balance feature importance. And it seems that'd be a cool thing for someone to work on, is to try to modify the split selection thing, where you can sort of try to balance feature importance to basically have flat feature importance or something. But that would, yeah, you'd probably have to get into the guts of a tree learning algorithm, where you basically have sort of the running total of your feature importances, and you sort of bias your splits to use features that have like currently low feature importance to try to balance it or something.
Right. Right, that's all I have.
Cool. Yeah. Thanks for the questions and comments. Anyone else have anything they want to talk about before we wrap? Because we're coming up on the hour. No? Okay, guys. Well, thanks so much for everyone who showed up. Please give us some feedback in Rocket Chat or by email or whatever. Please, yeah, let us know what you'd like to talk about in the future. And post any questions to Slido. It's a lot of fun talking to you guys and talking about this paper. I'm curious to see what if this changes your thinking on anything. And if you have any further questions, yeah, but just post them in Rocket Chat and I'll try to respond to all of them. So thanks a lot and see you guys next time.
Oh, this guy just
So
got
you
let
think
go.
you know Wix, but do you really?
Oh, don't know Wix. Okay, let's figure this out. So, yeah, sorry, for the remainder of this stream, I'm going to be doing some environment setup. You're welcome to join me, but this might be kind of basic and boring, but might as well do it now. In fact, actually, let's not do that. We had 2.5 hours. So yeah, we're gonna call it. I think basically what we did figure out here is the basics of what this is all about. Machine learning and predicting stock market returns on data, just raw data. The main thing I wanted to finish off here with is just to scan through the rest of this tutorial to see what else is going on. So let's see. Yeah, they're going to just do some evaluating of the performance, looking at some correlations for MMC. This is what they were talking about in that YouTube video. What is core all about? Oh, wow. Okay. Cumulative validation of core, of MMC, different performance metrics, and then submitting to actually compete. Okay, so that's what we're going to do. So after get this set up, let's maybe in the next episode of this, we'll do some more analysis of what the data actually looks like. See if I can get my feature versus performance bar going. Then we submit and see how it goes. Cool. Okay, so until next time. Thank you and goodbye.